So we've discussed how analytic functions satisfy this Cauchy-Riemann equations, and somehow the real part and imaginary part of the function is intertwined. In this video, I like to prove some facts about analytic functions, and this example has three purposes. One is that it's a useful fact that we're going to be using later. Number two, it gives us an example of how you might use Cauchy-Riemann equations to get some information about analytic function. And number three, hopefully this example gives you more intuitions about how function has to behave as an analytic function. Anyways, let's get right to it. Okay. So I want to prove a couple conditions that can show that analytic function has to be constant. So let's say you have an analytic function on a connected open domain D, and if the derivative is equal to 0 for all points in the domain, then f is a constant function in that domain. So hopefully this is not too surprising because that's true in the one-dimensional case, right? If the derivative is 0 in an interval, then it has to be a constant function. But let's try to use Cauchy-Riemann equations and also use this one-dimensional fact to see if we could prove this for the analytic function case. Okay, so here's the idea of the proof. First, we're going to show that function has to stay constant in a disk. So we're just going to look at a disk. And if the derivative is 0 everywhere on the disk, then it has to be constant on that disk. And then on step number 2, we'll extend this idea to any open connected domain. So let's see how we might do this. So let's say we have the derivative equal to 0. Note that the derivative could be written in this way. Right? It's the derivative is the same in any direction you take. So it's true that the real part and imaginary part, if you take the derivative with respect to x, we get 0. So if we start at A and we travel to point B, that's on a horizontal, I guess on the same horizontal level, using the one-dimensional fact that the partial derivative of both u and b has to be 0, u and b has to be constant on that line segment from A to B. Okay. Also, from B to C, along that line, we also know that derivative of u is also equal to 0 along that line. So along the vertical line, the function has to be constant. And since it had to be constant from A to B and B to C, the value at A to C has to be equal to each other. But C could have been anywhere on this disk, right? You can get any other point on this disk by first moving horizontally and then moving vertically. Okay. Now, what we do is we're going to extend this to any domain that might be much more complicated looking than disks. So we're going to use this fact that we had from topology, that if you have an open connected domain in a complex axis, then connected means it's also path connected, right? So if you have any 2 points A and B, you can connect it with a path. And this domain is also open. So anywhere along this curve, I could draw some circle for each point along that path. So you could have infinitely many circles, but also you could actually cover the whole path with finitely many disks as well, right? If that's true, we know that the function has to be constant within each disk. So we can kind of travel through overlaps of the disks in this vertical and horizontal segments to reach to point B, showing that the function value could never change along that vertical and horizontal path connecting A to B. Okay, I hope that made sense. Okay, so I think that theorem isn't too surprising, but this theorem, if you use it correctly, you could prove much stronger statements about analytic function. So here's a couple. So if you have an analytic function f, where the u and v is the real and imaginary parts of the function, and suppose you know one of the function is constant. So let's say u. Okay. Then the whole function f has to be constant, even before looking at what the function v is doing. Okay, well, how could that be? Well, if u is constant, then the partial derivative with respect to x and y of this function is equal to 0 everywhere. And Cauchy-Riemann equation says that, well, if ux is equal to 0, then by is equal to 0. And if uy is equal to 0, then negative vx is also equal to 0. So the derivative on u restricts the derivative on v, and now we have derivative is 0 everywhere. So using the previous theorem, we have the function has to be constant. Okay, you could go even further as well. So maybe you don't know that u is a constant function, but let's say the modulus of the function is constant. This also implies that analytic function is constant. So let's see how we might be able to prove something like this. Okay. So we can write down the modulus square of the function. Oh, I think I forgot a square in the statement there. So let's say we have a modulus square of the function that's the real part squared plus the imaginary part squared, and that's equal to constant c for some non-negative value c. If c was equal to 0, then the only way this could be 0 if both real and imaginary parts are equal to 0 everywhere. So we already get that it's a constant function. If c happens to be positive, then what we could do is we could take this equation and start taking some partial derivatives. So if we take derivative with respect to x, we get 2u times ux by the chain rule, and 2v vx equal to 0. 0 because derivative constant is equal to 0. And if we take the derivative with respect to y, we'll get something similar. So from this equation, we could use Cauchy-Riemann equation. So what we're going to do is we're going to try to put everything in terms of u. So vx is the same thing as negative uy. So we're going to substitute that. And vy is the same thing as ux. So we're going to substitute that. If we do that, we're going to get these two equations. Okay. From here, the equations are starting to look similar. We have few unknowns, but what we could do is we can kind of multiply by the right thing and cancel parts that you don't want out. So what you could do is you can multiply the first equation by u and second equation by v. If we do that, then some terms are going to cancel out. So uv uy and uv uy here with a negative in front will cancel out if we add the two equations together. What we're going to be left with is this expression, u squared ux plus v squared ux. We can factor out the ux, and u squared plus v squared, we know that's a constant, c. And we know that cux is equal to 0. So that tells us that ux is equal to 0. You could actually do a very similar argument and show that uy is equal to 0. So what you're going to have to do is to multiply u over here and v up there, and then subtract the two expression, and this time cancel out the ux terms, and then solve for the uy terms. You'll get a very similar expression. Okay, and if you show that ux and uy are both equal to 0, we could use the previous theorem, saying that if u is constant, then the whole function is constant. Okay, what do you guys think? So being analytic constrains you quite a bit. You can't even have a function where the modulus is constant. We'll dig more deeper into the meaning of what it means to be an analytic function, and we're going to have a more geometric answer soon. But anyways, I think I'm going to end the video here.